Okay, in this video I'm going to talk through the first example problem in this handout that I gave you the link for, more maximizing revenue problems. Before I start the specific problem, I just want to point out that at the top here are the general instructions which refer to the process you'll go through for almost every one of these maximizing revenue problems. Very often first you'll need to write a linear demand function. So that tells you usually the number of items as a function of the price. So there will be enough information in the problem so that you can figure out this linear expression that's in the form y equals mx plus b. Then you will need to write the revenue function, which is going to end up being a quadratic. And as a quadratic function, remember it's going to be a parabola, and in fact specifically it will have a negative leading coefficient. So it will be one of these concave down parabolas that has a vertex which is a maximum. And that is actually going to be the third step. We're going to need to find at least the x-coordinate and often both coordinates of that vertex so that we can answer the questions in the problem. And then sometimes in addition we need to be able to calculate the number of items that would be sold at that maximum revenue level. And in that case, you would go back to the linear demand function you did at the beginning to answer that question. So, but we're going to illustrate all of these steps on problem number 1. Problems 2, 3, and 4 don't ask for every single one of these things. So part of what you'll do in problems 2, 3, 4 is to determine exactly what you're being asked to do and then select from these different steps in the process what you need to do to answer the questions. Okay, let's look at number 1. The problem says a gardener currently grows 750 prize-winning roses each season and sells out at a price of $20 each. A survey of his clientele shows that for every $2.50 increase in price, 25 fewer flowers will be sold. So the first thing it asks us to do in letter A is to write the linear demand function, giving the number of roses sold as a function of price. Okay, so remember that when we have this kind of expression, one quantity as a function of the other quantity, that this right here is your x, your independent variable is the thing, the quantity that you are writing it as a function of. Okay, and then the number of roses is y. That's the dependent variable. So the idea is that once you know the price, then you can figure out what the number of roses is. Okay, so let's start a little T-chart. I'm going to move this off to the side so I can start doing some work here. I'm going to write down the given information and use it to help me write a linear function here. It tells me in the problem, let's move it back where I can see it, that he sells 750 roses at a price of $20 each. So that is a pair of numbers that can go in my T-chart here. The price, X is the price, is $20, and at that price he can sell 750 roses. So Y, the number of roses. Now, let's use the information in the problem to get another pair of values, another point on our line. It tells us a survey of his clientele shows that for every $2.50 increase in price, 25 fewer flowers will be sold. So if I were to increase this by $2.50 up to $22.50, then that would decrease the number of roses by 25. Down to 725. Okay, so now I have 2 points. Once I have 2 points, I can always write the equation of a line. So first I'm going to figure out my slope. Remember that slope is going to be the difference in the y values up top in the numerator divided by the difference of the x values. So it's going to be the change in y per unit change in x. In this case, it's going to be the change in the number of roses per dollar, since price is our x's. The numbers that go in there are the ones that are in our table here. So if I think of the top line as my first point and this bottom line as my second point, then y2 minus y1 is 725 minus 750. x2 minus x1 is 22.50 minus 20, and that comes out to negative 25 over 2.5, which comes out to negative 10 over 1. It actually reduces. So notice that this slope, as we just said, is the change in the number of roses per dollar. So when we see it in the unreduced form here, it looks very familiar, because this is what we were told exactly, that there will be 25 fewer roses sold for every $2.50 increase in price. But that is equivalent to saying that there will be 10 fewer roses sold for every $1 increase in price. Okay, these are equivalent fractions. It's just the negative 10 is a little bit simpler, so that's the one we'll use in our formula. Okay, so far what do we know? We know that the slope is negative 10. I still need to figure out the y-intercept. Frequently we do this by taking one of the pairs of values xy that we know and substituting into the equation. So let's use x equals 20 and y equals 750. Substitute in, and we find that b is going to be 950. Okay, so now I have my equation. I can say that y is equal to negative 10x plus 950. Remember that y is the number of roses and x is the price per rose. Okay, so we've done part A. This was all part A. Part B asks us to write the revenue function. Okay, and at the top it reminds us that the revenue function is always going to be price times the number of items sold. So revenue equals price times, in this case, the number of roses. Okay, well, price is just x, so I'm going to substitute an x for that part. Number of roses, I want everything in terms of just x. I don't want to use y for the number of roses. So notice over here that y, the number of roses, is equal to negative 10x plus 950. This is what I'm going to put in for the number of roses. Okay, so now I have the revenue in terms of just one variable, x. And to make it just a little bit easier to do the rest of the problem, I'm going to multiply out. So revenue, which we might write as r of x, is equal to negative 10x squared plus 950x. Again, remember x is the price. Okay, now we're ready to go on to part C. It says find the price that will give the greatest revenue per season. So let's move down a little bit. Remember that this function here, if we were to graph it, would be a concave down parabola. X, the price, would be on the horizontal axis, and the revenue would be on the vertical. Okay, so if we're looking for the price that will give the greatest revenue per season, well, the greatest revenue occurs here. And the price that will give us that greatest revenue is the x value that corresponds to that point. So in other words, we're looking for the x coordinate of the vertex. Well, I have a formula for that. The x coordinate of the vertex is always negative b over 2a. Always, for every problem. So when I want to know the price for max revenue, I need to do negative b over 2a with this function I have right here for revenue. Negative b is negative 950. 2a is 2 times the negative 10. And when I substitute those values in and do the calculation, here's my calculator. I'm going to say 950 divided by 20, and it gives me 40 and 50. Okay, so the price for max revenue is $47.50 per rose. Okay, so that's letter C. We have finished that part of the problem. In letter D, now it asks how many roses will be sold at that price. Well, for that, we need to look back here at our demand function. The number of roses is equal to negative 10 times the price plus 950. Okay, so the answer to letter D, the number of roses at max revenue, is going to be negative 10 times, there's your x value, 4750, plus 950. So let's use the calculator again. See what that is. 10 times 47.5, okay, that's actually a negative 475. So negative 475 plus 950. That doesn't seem right, does it? $475 per rose. I think, no, that's not what that means. What does it mean? It's the number of roses. That's right. Okay, I got myself confused there for a minute. We already figured out the price. The price per rose is $47.50. And remember, in letter D, we were figuring out how many roses would be sold at that level. And so 475 roses would be sold, which is fewer than, remember, he had been selling 750 roses. But we're not trying to maximize the number of roses. We're trying to maximize his revenue, how much money he brings in. Okay, so now we've got the answer to letter D, the number of roses at max revenue. Finally, in letter E, it asks us, what will the max revenue be? Okay, so that is going to require us to go back to our revenue function, right up here. R of x equals negative 10 times x squared plus 950x. And we're going to plug in x equals 4750. Remember, that's the x-coordinate of this vertex. If we were looking for both coordinates, so far we just have the x-coordinate. Now we're going to find the y-coordinate. So I could write it this way. It is r of 4750, which means I'm going to substitute 4750 everywhere there's an x in my function, in my revenue function. Make sure you get it in both locations there. And now I'm going to bring the calculator over and say negative 10 times 47.5 squared plus 950 times 47.5, enter, and this is my revenue, $22,562.50. All right, so that is the total revenue, and that is going to be more than what he had been making before. We didn't calculate what he made before, but we could. Think back to the very beginning. The very beginning, he was selling 750 roses at $20 each, right? So he was making $15,000 in revenue, and now the max revenue is more than that, $22,562.50. So that's the y-coordinate up here, 22,562.5. Okay, so that's how you do all the parts of these maximizing revenue problems. I will be posting the answers to numbers 2, 3 in a couple days, but in the meantime, try and go through these steps and apply them to those remaining problems.